so we're going to continue with our SAT prep unit for Honors Algebra 2 Pre-Calc. Right now we're working on one of the other problems from the pre-test, which is 1.6.14, which again means that we're using practice test 1, section number 6, and problem number 14. This is a grid-in problem, meaning that you have to actually generate the answer. There's no multiple choices. So the problem says, exactly 4 actors try out for the 4 parts in a play. If each actor can perform any one part and no one will perform more than one part, how many different assignments of actors are possible? So there are 2 ways to do this problem, and one of them is much faster than the other. So here's the idea. I have 4 different parts, right? Part number 1, part number 2, part number 3, part number 4. I have 4 people, right? There are 4 people that could play the first part, right? So if this is my first part, there are 4 people that could play it, right? But because one of the 4 is chosen, there are only 3 people that could be chosen for the second part. So for the second part, I have a 3, right? And because someone was chosen for the second part, for the third part, there's now only 2 choices, so that's 2. And for the last part, right, for the 4th part that the actors could play, I have to go with whatever guy didn't get picked already. So that 4th part is really just sort of the dregs. So the fundamental counting principle says that I take the number of ways I can do the first thing, which is 4, times the number of ways I can do the second, which is only 3, times the number of ways I can do the third, which is only 2, and then times that 1 way to pick the 4th part, and I end up with 24 ways to do this, which is the correct answer. The other way to do this, which gives you the same answer but is much more visual and is totally fine, it does require a little bit more work, is to actually make this as a tree diagram, right? So for my first part, right, I could have person A, person B, person C, or person D, right? There are 4 actors, A, B, C, D. But for the second part, right, there are only going to be those 3 choices because if I already picked A for the first part, I can't possibly pick A for the second part, so I'd only have B, C, and D. Or if I picked B, then I'd only have A, C, and D. And if I picked C, then I'd only have A and B and D. You can see already how this is going to get a lot worse. And if I picked D, then I'd only have A and B and C, right? But then when I get to my third part, well, now I've already chosen 2 actors, right? So for instance, A and then B, well, that must mean that I only have choices C and D, right? And then for the next one, I already have A and C, so I'd only have B and D. And then for the next one, I have A and D, so I only have B and C, right? And then the same thing happens here. So what you can see is that this one person has already branched out into 1, 2, 3, 4, 5, 6 possible outcomes, right? And then the trick is that from here, I don't have any choice. When we get to the 4th part, right, if I were to keep going with this, when I get to the 4th part, I have to pick, if I already have A, B, C, I have to pick D. If I already have A, B, D, I have to pick C. There's no branching. For the last part, you have no choice left, right? For the last part, you just have to go with whoever's left. So what I want to point out is without drawing this entire ridiculously huge diagram, if you just look at what happens if I picked A first, just A first, A, B, C, D, A, B, D, C, A, C, B, D. Sorry, my brain shut down a little. B would be the leftover guy, C would be the leftover guy, and B would be the leftover guy. So if you notice, there are 6 total outcomes if I picked A first. If you continued to make this ridiculous tree diagram that would make you somewhat miserable, you'd get 6 outcomes for B being the first actor, 6 outcomes for C being the first actor, and 6 outcomes for D being the first actor, which is why it's not surprising that we get 24.